You have singularities and gauge theory. Singularities, they come across all over physics and mathematics, and usually people like to think of singularity as a problem. I always like to say that singularity is an opportunity. So, first of all, I'd like to acknowledge the fact that many other teams are working on similar questions and having great contribution. And I'd also like to say hi to all my collaborators. So for the menu today, we are in a dining room, if I understand correctly. So we'll talk a little bit about geometry and gauge theories, how our representation theory will come to save the day. We'll talk about our singularities, and we put everything together. So all the words that I mentioned here, if you go to my restaurant, you can also say, I'm just going to take the combo, and the combo would be the elliptic fibration. So basically, we are talking about the tale of two worlds. So I know everybody like watching Game of Thrones. So you have two kingdoms. Each of them have different rules. And so what we're talking about here is how to match the rules of one kingdom with the rules of another kingdom. So I will start first with the physics, and then I'll go, without apologizing, on the mathematics side. So there are different physical pictures that are relevant to understand this story. But the 5D supersymmetric theory with 8 supersymmetry are the one in which the picture is easier to understand. So you can get that theory from M theory by doing a compactification on a Calabi-Yau threefold. So the type of multiplet that you have is the gravity multiplet that we will safely ignore in the beginning of the talk. Then you have vector multiplet that will play a central role with hypermultiplet. You can also have tensor multiplet in this theory, but if they are not charged, they just dual to the vectors. So now, if we think of the geometry of this multiplet, vector multiplet, they are characterized by what is called very special geometry. The reason why it's called very special is because if you do the same thing in 4 dimensions, you have special geometry. And so you have special geometry and another geometry which is also special, so they just call it very special geometry. So now on the hypermultiplet, if you have gravity, you have a quaternionic Kähler geometry. And if you go to the limit in which gravity is irrelevant, you get an hyperkähler geometry. And the link between the two is essentially that the gravity, the Newton constant is related to the curvature of the quaternionic Kähler manifold, and when you decouple gravity, it becomes hyperkähler. So now let's try to start talking about singularity. So this is the prepotential that you see in 5D dimension, and we don't really need to understand this expression except to see that you have absolute values here. And this absolute value, they involve scalar products, essentially the hyperplane defined by roots. You have a gauge group, so you have roots. And then you have representation and you have weight. And the hyperplane defined by the roots and the representation are singularity of the derivative of this expression. So if you go to the Coulomb branch of the theory, essentially, you have just abelian symmetries. And because your gauge group is broken to the abelian part, you essentially live in a Weyl chamber. And the roots define the wall of the Weyl chamber. And the representation, you have to think of the Weyl chamber as this room. And the representation, through the weight, they introduce additional walls inside the Weyl chamber. So at the end of the day, you end up with a structure that very look like an apartment with different rooms separated by walls. So now we want to describe a geometry using this mathematical object. So we have a Lie algebra with roots and a Cartan subalgebra, and we have a representation. So the roots and the weight of the representation define wall and define chambers and subchambers in the Weyl chamber. So now we do a very big move. So we were talking about things that have to do essentially with representation theory. And now we talk about geometry. So elliptic fibrations have vibration of genus 1 curve. So usually when we call them elliptic, it means that you choose a point on the curve. And when you do that, the curve becomes a group, and it has a very beautiful way to describe the group. For example, when you play with cubic curves. So elliptic curves, they are one of the oldest objects studied in mathematics. I guess if we go back to the 3rd century, we will be talking to people who know what are cubic curves and that have actually used some of the curves that we actually work on today. So today I was emailing one of the students at Harvard with who I work, Patrick Jefferson, and I mentioned to him that one of the elliptic fibrations he's working on has been actually introduced in a book written by Diophantus in the 3rd century. And Diophantus gave a problem, which is just a number theory problem. Take a number, subtract with another number, and then it's like the square and the cube of whatever other number. And if you write that equation, you end up with the elliptic vibration he's working on. So just to say that this is extremely beautiful subject. And again, last week I was in Princeton, and I was in a conference full of people who do cryptography, including people from the NSA. Why not? And they mentioned to me that they came to my talk because it was about elliptic curve. I don't know, it was just a weird feeling. But anyway, I wanted to mention. So they also use in geometric design and in physics. So this is an elliptic vibration. So you have a total space, a base, and the elliptic curve is moving over the base, and as it moves, it can have singularity. So this is the typical equation for an elliptic curve. It's called a Weierstrass model. So any genus 1 curve with a section, even if it comes in family, can be written in this way. And so let's see quickly the geometry of this. So you could complete the square. So just to have like, describe it as the double cover branch at 3 different points. So we could play with a picture and show that this would be a torus. So now this torus vibration has singular fibers, and the history of the study of the singular fibers of elliptic vibration is a really beautiful story of the history of mathematics. So it started with Kodaira, who wanted to study and classify surfaces. So in the list of surfaces he could classify, elliptic surfaces were playing a special role, and so he has to consider them as a special case. And he classified all the fibers that we will see in another in the next slides. Then they can be expressed as Weierstrass model, and that's usually how they are studied in many questions of number theory. And this curve, they can have Néron models, which characterize also some aspect of their geometry. And to classify the singular fiber, you can use an algorithm that has been popularized in string theory by Morrison and Vafa, which is called the Tate algorithm. Then you have singularity that happens in codimension 1. And as we will see next slide, they're extremely beautiful singularities, but then they can collide in codimension 2. And when they collide, you have this collision of singularities that have been studied by Miranda for elliptic threefold, and then it has been generalized by Slidlow, who was a PhD student at Harvard working with Barry Mazur, and now he works on elliptic cryptography. Okay, so these are the singular fiber of an elliptic vibration. So as you can see, this curve, at least those that are on the right side, are very familiar because they are extended affine, or people call them extended or affine linking diagram. Those that are here, usually people have a hard time to describe them, but they're actually very natural, as we will see in a moment. So there is a duality between these curves. So all the exceptional groups for which we recognize the linking diagram are actually drawing away to those curves that are here. So this is a nodal curve. It's essentially a torus that is pinched along a circle. This is a cusp that you can construct by taking the nodal curve and making the two tangents coincide. This, you can think of it as the intersection of two quadric a quadric on a line that intersect as tangent, and this you can think as three lines meeting at a point. So now let me talk about collisions of singularity. As you can see, so we have this singularity that can show up in codimension 1 of an elliptic vibration, and they can collide, and when they collide, this becomes, in some sense, chemistry, and you can see what happens at the intersection. So you have to think of two divisors that have each singular fiber on each of them. They collide, and that's the collision, you expect to see something. So let's describe this situation. So we have, for example, fiber of type 2 and fiber of type 4, and you can ask yourself what happens when they collide, and this is the answer. You get a fiber that essentially looks like two spheres that intersect with multiplicity 1 and 2. So one thing that you see with the collisions don't necessarily have the typical shape of extended Dickinson diagram. So, but we will understand them as related to certain representation. So another point that is important to see, when you have collisions, you actually deal with resolution of singularities, and it's highly non-trivial. So for example, it's not something that commutes. So if you think of type 4 intersecting type I star 0, when you do the resolution of singularity, if you first consider the resolution of one and then the other, you get something different if you do it in the other direction. And so this will be related to the fact that when you have collision of singularities, you can have more than one resolution of the same space. So this geometry here is the geometry of an elliptic vibration with a general cubic. So a cubic is an equation of degree 3. So you can think of how it can split. So it can have a singularity which would be an ordered curve or a cusp, and then it can decompose. So if the cubic factorizes a quadric on a line, you have this expression here. A quadric is described by the circle. It intersects the line at 2 points. If the line becomes tangent to the quadric, you have this other type of singular fibers and so on. So this is the case when you, the cubic split into 3 lines, and the 3 lines intersect at a point. All these fibers that are on this side of the table are actually Kodaira fibers. They could show up in codimension 1 of an elliptic vibration, whereas the 2 that are on the other side are not in the class of Kodaira fibers, but they also are interesting. So, okay, so now we will put these two stories together, and so I will start with the following gauge theory. So I take an SU2 gauge theory with fundamentals hyper multiplied. So if I have that, geometrically, what I get is essentially this geometry. So I have this picture that represents SU2. So this is a Kodaira fiber of type I2, and it can degenerate in 2 ways. So when it degenerates such that the 2 components become tangent to each other, I don't produce any matter at all. But when it degenerates as a composition of 3 lines intersecting as a I3, fiber of Kodaira type, this represents an SU3. So if you think of the enhancement of SU2 to SU3, you understand that the decomposition of the Lie algebra will produce the fundamental representation. So that's how what you see in the gauge theory side. And the Coulomb branch of this theory is kind of boring in the sense that there is only one line with a starting point and no chamber at all. So the next case we will consider is the case of SU3, also with fundamental matter. So in this case, the Coulomb branch is very different. So we have these 2 chambers here, and you see that these are basically the walls described by the roots, and this is one defined by the weight. So these 2 chambers, each of them, so the interior side of each chamber, represent a phase of the gauge theory. And the wall is a subsystem in which you have extra matter that become massless, represented by the hypermultiplet. And so to go from one to the other, you have to pass through the wall. So then these 2 chambers they also intersect at a point which is like the origin of the Veil chamber of the Coulomb branch. So now, let's see what happens if I use exactly the same system. So I use an elliptic vibration that represents an SU3, and I try to resolve the singularity. So this will represent my original Weierstrass equation, and it has singularity in different codimensions. So to blow up that singularity, I have to do it in 2 steps. But after the first step, I have 2 different ways to resolve the singularity. And these 2 different ways, they are related by a flop transition. So you have one curve that shrinks and show up on the other side as a different curve. So now this is the geometry of SU3 if you think of it in terms of the fiber. And again, so you see how SU3 enhances to SU4 and give you fundamental matter. Here, this doesn't generate different type of matter. And you have also this nice SO8 that show up in codimension 3. In an F-theory context, you will actually make sense of that fiber as well, because it will give you information on the Yukawa of your theory. So now here is the first match between the geometry and the representation theory. So let me insist that this side of the picture were obtained essentially using representation theory. And this one is the result of a resolution of singularity. So now let's try to match each side and understand the correspondence. So the origin of the Veil chamber corresponds to the original Weierstrass model that we try to resolve. Then the chamber that we have on each side, they correspond to the full resolved space that we obtain at the end of the resolution procedure. Then the wall between the 2 chambers correspond to the partial resolution that we have. And so if you sit on this wall, you could resolve by going on the top and at the bottom, and this is clearly represented here. And then the flop transition, which is the geometric transition between the 2 resolutions, correspond to crossing the wall on the representation theory side. And let me just say that this geometry is relatively simple. To do the resolution, it will take you about 15 minutes. Am I trying to be positive here? With that minus sign mistake, that's about it. And whereas the other side can be done in a matter of 2 minutes. So the effort that you do to have exactly the same answer is kind of ridiculous. Like representation theory really gives you an insight into this geometry. But because the geometry is relatively simple, it's not so much of a big deal. So let's go to something more complicated. It is a perfect match. So this is the incidence geometry for SU4. So SU4 has a rank 3, so this is a 3-dimensional geometry. And so again, so this is the origin of the Veil chamber. And you can clearly see how the Veil chamber split into different sectors because of the hyperplane defined by the roots. And you have 1, 2, 3, and 4 different chambers. And each of these chambers, they are separated by walls that are defined by the roots. And then all the walls intersect along one line that goes all the way to the origin of the representation of the Veil chamber. So this geometry, I think we will agree, is highly non-trivial. And it's a simplicial geometry. You can really use the tools of like incidence geometry to describe this. So here is a slide of the same thing, so that you see the 4 chambers that you have, and you see the walls between the chambers and the common point where all the walls intersect. So now the point is to try to describe everything that you see on this picture from the point of view of the elliptic vibration. And this is what you get. So these tree represent all the different ways you can resolve the geometry. So after the first step, you have 3 different ways to continue, and for each of them, you have 2 different ways to finish the work. So the first thing that you see is that it doesn't seem to be a match, because here we have 1, 2, 3, 4 chambers, whereas here we have 1, 2, 3, 4, 5, 6 different resolutions. So what happens? So what happens is that some of this resolution are actually isomorphic to each other. So after the resolution procedure, you have to identify those that are the same, and then you can draw a graph that take into account this identification, and that's the graph that you get. So now we have 1, 2, 3, 4, so it seems a little bit more familiar, but we see that in the previous step, we have like 3 partial resolution. But if you look again, this picture, we had 3 walls inside the veil chamber. And finally, this represents the line where all the walls meet, and this is the origin of your veil chamber. So geometrically, this is what you see when you resolve the geometry if you look at the fiber. So SU4 enhanced to SU5, and then you see that here you also have matter as you have an enhancement to an SO10. And interestingly enough, you also see that there is a new type of fiber which is not in the family of Kodaira. So depending on your interest, you can focus on this picture if you want to classify singular fibers, or you can focus on the set of resolution if you're interested in matching the gauge theory. And so that's the picture that summarizes everything. So let me again match. So you have the original singular geometry that corresponds to the origin of the veil chamber. You have the partial resolution number 1 that corresponds to this line. Then you have the 3 partial resolution at order 2 that correspond to these walls. And finally, you have these 4 chambers, these 4 resolutions that correspond to these 4 chambers. And this represents like the higher intersection of the walls. So now, if I want to do this for a bigger group, let's say I'm working with, I don't know, SU10 or whatever, I'm going to do exactly the same thing, except that the tree will really grow and becomes a really enormous tree. On this side, it's still going to be exactly as simple as before. So this is the case of SU5. So SU5 is studied for many reasons. One of the reasons is because it's the group of ground unified theory. So when you want to do ground unified theory with SU5, you have to deal with fundamental and anti-fundamental representation. And when you consider all the possible chambers that you can have, you have 12 of them, and they represent the following geometry. So we are working on giving an algebraic representation for each of these chambers, which we did, and the team of Sakurai is also working on the same question. So now I'd like to say something about this structure. So first of all, there is a Z2 symmetry where essentially each node has a matching wall on the other side of the diagram. So in many descriptions in the literature, the meaning of this Z2 symmetry is not really understood properly. And the best way to understand why all the picture we have such a Z2 symmetry is to go back to number theory. So when you have an elliptic curve, as I said, it has a group structure, and that group structure always have a Z2 that corresponds to sending an element to the opposite element in the group. So when you do the resolution of singularities, like here, this Z2 symmetry match these two guys. And it's a symmetry of this partial resolution, but when you blow up a further step, that symmetry is broken, and what used to be a symmetry inside the space become birational transformation between different spaces. And so that's the graph that you have. So I'm going to finish the talk here, but first I'd like to make a comment about conditions that I usually assume in the physics literature. So when I talk about the SU5, when I talk about the 5-dimensional gauge theory, I mentioned that you had to do a compactification on the Calabi-Yau. But actually, when I do my resolution, I never use the Calabi-Yau assumption. I don't need the space to be necessarily 3-dimensional. It could be a 4-dimensional elliptic fibration, and I will also do exactly the same resolution. So what it means is that everybody agrees that we don't know what string theory is, but what we know is what it can do. And one thing that it can do is that sometimes it can open a window into something for which it has a certain understanding of the rules, but this understanding might just be very small compared to the reality of the room on which it gives you a window. And I think for resolution of singularity, this is really the story. You could use representation theory even in cases where there is no meaning in the string theory language, and still have a match between things that you can compute using representation theory and those that you can compute using string theory. One technical comment about this graph is that it's very important to realize each of these resolutions as projective spaces. So when you have a projective space, you end up having a lot of theorems of algebraic geometry that work on your favor. One of these theorems is, for example, on the Calabi-Yau case, all projective resolutions, credpoint resolution of the same space, they have the same odd numbers. So they will have the same Euler characteristic, and a lot of other invariants will match. If you allow yourself to not consider only projective resolution, but just do analytic flops, then you will not have a way to define when you have to stop doing your resolution, because analytic flops will allow you to do much more than the 12 rooms that you see on this picture. So I'm going to end here, and I'd like to thank you again.